My name is Kusha Raisi. I'm a doctoral research assistant at UMass Lowell, and today I want to talk to you about my poster titled Ground Penetrating Radar Detection of Steel Rebar Corrosion in Concrete Specimens. As for the introduction, we all know that concrete rebar corrosion is a very important safety risk. It's a major infrastructure issue in the United States. It induces section loss and stress concentration, which subsequently leads to cracks and spalling. As you can see in figure 1, we have 4 stages of concrete cracking due to rebar corrosion. So the first stage, the specimen is intact. In stage 2, we have depassivation, which happens when there is a high concentration of chloride ions around the rebar, and the passive film breaks. And we have initiation of cracks, and at stage 3, the cracks have advanced to the surface, so we can basically see the cracks. And the last stage, which is the spalling, we can see that the concrete specimen or infrastructure is opened, and we can see the reinforcement. We call that spalling. And the specimen is hopeless and helpless at that stage. And it will be very costly to repair these, because as you can see from stage 2 to stage 3, visually we cannot see anything. So we need these methods, we need non-destructive testing methods in structural health monitoring. So we can monitor and identify these issues, specifically corrosion issues, before they reach a critical point, and they can cause safety hazards on top of that due to sudden failure of the structures. So our objective is to assess the feasibility of a device. We have a 1.6 GHz GPR for corrosion detection and quantification. And by observing the changes in the geometry, that is the scattering response that we get from the radar, and the amplitude, which is the reflection strength, we want to study the impacts of the scan position and angle as well when we want to assess the feasibility of the GPR. So in order to do so, we set an experimental grid. So we have 3 specimens. We casted them back in 2017, and they're 12 by 12 by 5 inches. They're RC panels. They all have the same size of rebar at their center, and 2 of those specimens were used in the accelerated corrosion test in a controlled laboratory environment at UMass Lowell, and 2 of the specimens reached stage 2 and stage 3 of corrosion respectively. So as you can see here, at stage 3 we have a surface crack along the length of the member in the middle on top of the rebar exactly, and at stage 2 they're very similar, except that we do not have any surface cracks. And stage 1, of course, for baseline, there is the intact specimen. And the GPR device has a value called the dielectric constant, which we set it to 5. And as you can see, the B-scan image of a GPR is basically a 2D slice through the specimen. And it is made up of a finite number of 1D curves called the A-scans, as you can see here. And the rebars, because they're circular, they're round, and they're perfect electric conductors, they're seen as these very strong hyperbolic shape responses. And this is the jet color code, hence the blue and red colors to indicate negative and positive. And this is the background signal. As you can see, it starts with the positive and the negative strip lines, and we will get to that in the next column. And as for our scans, we have to analyze the effect of 2 important variables. One is where, the position of the scanner with respect to rebar, and one, the angle of scanning. So in order to do so, we scan at 6 different angles: 0, which is vertical to rebar, 30 degrees, 45, 60, 75, and 90, which is perpendicular, which is the ideal scan angle for locating rebars. But we want to see what we can see and quantify nevertheless. As for results, we start at the top, at the surface of each GPRB scan. We compare the three horizontal B scans that we got at the top, at the middle, and at the bottom, because we need to study the corner scattering effect. We want to see if being so close to the edges actually distorts our image and changes anything, and that might change important parameters in our results. Therefore, we look at the background signal. As we can see here, we have the middle scan, the top scan, and the bottom scan, corresponding to these three scan lines here: one, top, middle, and bottom. As you can see that we use this equation here, which is the range values that correspond to the local maxima of these radar amplitude points. As you can see, we have the effect of double corner scattering here after modeling this pattern, because in the middle we only have one scattering, which is this one. As you can see also here, one corner scattering, but we have double corner scattering for the top and bottom scans. So it is determined that the scan that is farthest away from the edges is mostly ideal. As for the angles, as you can see, the hyperbolic shape becomes wider as the angle becomes smaller, and it reaches basically infinity when it reaches 0. And this is true for all groups, for stage 1, stage 2, and stage 3. So using a second order contour and second level contour and equation 1, we modeled them, and we defined something called the characteristic width coefficient, which is the inverse of the first coefficient of x squared in our polynomial, which we modeled to our points. As we can see that there is an exponential relationship, and also we can see the distortion in the geometry due to the surface rust. As you can see, for 30 degrees, 45, even up to 90, but it's hard to see because the numbers are so small. We can see that for each specimen group, the characteristic width is different, and for group 1, group 2, and group 3. We have that for group 2 and group 3, which are at stage 2 and stage 3 of corrosion. We see that the characteristic width is significantly smaller. Then we use the average curvature of the fitted curves, and we have a very good linear relationship between the angle theta and the curvature of the modeled hyperbolas using polynomial equation. And we can see the equations for K average and the characteristic width here, and the coefficient of determination is satisfactory. And after this, we can move on to what we actually wanted to do, which is the impact of corrosion on rebar response amplitude. So we talked about the combined effect of geometry and angle. So we know that in the middle, at the right angle, we have the best angling position and scanning position and angle. So in a single A scan on top of the rebar, we can see that the amplitudes in the phase change at the interface between the rebar and the concrete for stage 1, 2, and 3 are shown here. So for stage 1, the amplitudes are much higher than stage 2, and stage 2 is higher than stage 3. So it shows that when this corrosion process happens, the reflected amplitudes are actually not as strong as they used to be compared to the impact ones. And as for the local maxima points, that here we used the coordinates to model the background signal, but here we use the amplitude itself against the cross-range axis. So we can see the parabolic shapes again, and we can see that the stage 1, which is intact, has a higher curve, a higher data model, because the amplitudes are higher at any point that windows this hyperbola here. And as for the conclusion, as I mentioned, the best angle is the angle of 90 degrees to the rebar, and as farthest away from the edges as possible. And the amplitude and geometry is distorted. The amplitude is decreased due to corrosion, and the geometry is distorted, as we can see here again, because of the rust products that accumulate on top of the rebar, and they have different they have different electrical properties than the original steel rebar, and therefore we have this different scattering pattern. So therefore, by 2 parameter, geometry and amplitude, we can detect corrosion by using GPR in reinforced concrete specimens. Thank you.